All right, so welcome to today's class. So let's start with some discussion and see if you can cover any questions you have with the current assignment, which is kind of due by in another couple days. So this is a slightly lengthier assignment, so I extended I actually put in the original time for the due date to be a little longer. So any questions? Let's start with, let's go in order maybe. So I'll keep some structure. So any questions, Krishna Kamal?
Hey Pranit, actually the questions are a little, the question is a little bit confusing for me with the second part asking for like all the MSC and 5-fold cross-validation.
Mm-hmm.
So you already mentioned it's like a 5-fold thing, and in the function you're asking for like pass the number of folds. So are they two different?
Okay, so good point. The 5 would be just like an instance of a run of your function. So if you write a function that will work for any number of folds, 5 would be the instance for which you would run the example, for example, basically. Yeah, so that's the thing in there. Yeah. Any other things? Do you want me to dig anything deeper into the cross-validation, the technique? Not just the math side really, but because this is a more computational assignment, so more on the program.
Yeah, it will be great if you can just explain me about the MSC and
okay,
the cross-validation.
Okay, yeah, let's actually do that, and then we can jump to the next person's question, So maybe some of your questions will be common for the rest of the people, so a few things might keep getting clearer. Or
sure.
Your follow-up questions based on what I tell them.
Yeah,
okay,
thanks.
So yeah, let's do that. Okay, so this is a more of a computational way of looking at it. So let me draw, say, your data set or your data frame, and then let's break it into 1, 2, 3, 4. So you should
finish the screen, please.
Oh yeah, let's do that. You don't want to miss that part. You see my screen? Let's do.
Yeah. Yeah, Ben.
Yeah, good. Sometimes there's a time lag. Okay, so let's do something here. Okay, so basically, let's just draw a cartoonish diagram of the data set. So that's your data set. Let's break it into 1, 2, 3, 4. So you have 5 folds that you're breaking it into. Now, whenever I say a data set about this rectangle thing in here, it's basically, it has a bunch of columns, which are your variables, and one, you can assume it also includes the response variable as one particular column, so it could be the last column, or whatever the order, it doesn't really matter. And then you also have the rows are your samples, right? So if you have 1,000 sample data set with 100 variables, this is 1,000 by 100. We're also assuming you have more samples than the number of variables. That's why you have a longer thing going on in the cartoon. Now, so the k-fold, the process starts with breaking this down into 5 chunks. Now, do we just take the 1,000 row data set and break it into like 1,000 by 5, so 200 rows in each? So do we do 1 to 200 as first chunk, 200 to 400 as the next, and so on? That is not suggested. So what we do before even doing the data set is we shuffle the data set. So the data set basically is randomized, So let's call it shuffle routine, and then you get the data set, which is this data frame. Okay, so there's some pre-processing involved. Is that the only pre-processing? We're going to do more pre-processing too, but that's not the point here, right? We're going to do, say, scaling the variables or cleaning up missing values or throwing up useless variables if they're always constant. Because if a variable is completely constant, it doesn't tell you anything in distinguishing one row from another, be it for regression or classifying, right? So these kind of things. But so you have some shuffling after you have some pre-processing done. That's where the pipeline goes. The data set goes through pre-processing where you do all these missing handling and all that kind of stuff, cleaning up the data in structured form. Then you shuffle the data set. So am I shuffling the columns? No, I'm shuffling the rows. So the first row might end up somewhere. So it's like a uniform shuffle. It's like a uniformly random sample that you take from the data set. And then you also make sure there's no, when you shuffle, it's like done without replacement. So basically, it's just a shuffle. You're not going to get the same row repeating 30 times. It's not going to repeat even the second time. So it's going to be unique rows. Now we break it down into 5 folds. Now that you have some context, now each what row goes into each fold is also kind of picked randomly because you shuffle the data set. Then if you break it into 1 to 200, 200 to 400 in sequence, it's still okay because you know that the data has been already been shuffled. So each row has been randomly assigned to one of these 5 folds. So we split this into 5. So I will give you the picture first, and then I'll give you some tricks and hints that you can use with respect to the R to be able to do this process, because all this you want to implement. And this is a really good exercise to kind of brush up your R skills as well, a lot more. Once you shuffle it, the process is as follows. If it's a 5-fold cross-validation, so k equal to 5, there are at least 5 things you want to do. So the first thing you want to do is you want to drop the first chunk. So let me draw here. So you're going to drop this chunk out in the first iteration, if I can call it. So that's dropped. Now you're going to use this dropped chunk as your test data set. So it is dropped from training is what it means. So this is test. And then what you're going to do is this part, the rest of the chunks go into training. Okay. So that's the thing. Now you have a model from this trained chunk. Remember, there are 5 iterations, but this is just the first one. So all of this is just the first iteration, because the iteration, I mean, each time you drop one fold at a time as a test, you use the rest as the train. So you can go to the second iteration after this. It's going to be very similar, and then you'll get the feel for it. So let's see what we do inside this iteration. You use this as the training. So once you use this as the training data set, you obviously get a model, which, so after the training, right? This goes into training, and then you have a model, which is what we care about. Okay. Okay, you have a model. Now, what we do is you want to test this model. So what we do is, how do we test it? This is a predictive model, right? It is a mathematical or like a statistical model. The goal is to use it as a predictive model. So what happens is the model goes into, the model goes into a prediction phase. So where what you do is you pass the model into a prediction phase. Let's clean it up here. Let's do it here. So the model goes into a prediction phase. And into the prediction phase, what you want to do is you want to pass the test X. So the test X, which you put aside, you pass in the X into that. What is the X referring to? I am specifically referring to the input variables. So the X input. Okay. So the X input variables go in here, and the model is also going into the prediction phase. So the model is going here. So this is a predict function, basically, that takes in X and the model that you trained using and everything other than the first chunk. So this is going to give you predictions. Now those predictions you can compare with what the Y in the test chunk looks like. This is your Y variable, which is what you were trying to predict. So if you, to make it things a little more specific in terms of the X's and Y's that's happening in the training stage, in the training stage, you pass both X and Y because you want to train the model. This is training stage for training the model. You pass the X, all the input variables, and the output variable, which is this last column, for example. But you only pass it from the training chunk, so only from here. you trained a model, and then you have use the model to make a prediction on the test X, and you're trying to predict what's supposed to be here. But you know what the ground truth is, because this is a chunk you had with you before. You just put it aside. So this was not used in training the model or teaching or learning of this model. So now you have your predictions, and you have the true y's in this test chunk. So you can compare those. How do you compare those? Since this is a regression assignment, you just compute the mean square error. So this is a second question. But this is the mean square error on only this chunk. So all of this is just one iteration in the 5-fold cross-validation. You have to do 5 of what I'm telling till now. So you need to compute 5 cross-validation MSC errors, each on one of these test chunks. So let's do this chunk completely. So you have y predicted, and then you have ground truth, y ground truth, which this is the y ground truth, this is the y prediction that you made by looking at x only in the test chunk, but your model was trained on the training chunk, so it doesn't know anything about the test chunk. So how do you compare these? You subtract each entry in these variables. So you basically compute a norm of it. So let me tell you what a norm is. It's a very simple concept, at least in this context. You do a norm includes a square, actually. So what you do is you take the numbers in this, you take the numbers in these, you subtract them correspondingly. So if in the y prediction chunk you had yp, the first entry was yp1, the second entry, the first entry again in the corresponding ground truth. So this is the predicted first entry, this is the ground truth first entry, in the first sample of this test chunk, basically, right? So you subtract those, you square them up, and then now you generalize this. You do the same thing for the second entry. You subtract the errors, you square them up. So this is what you predicted. This is what it's supposed to be. You're trying to see how far it is. And you're doing the square because it could be far in a positive direction or negative direction. The ground truth could have been 5 for the first entry. You might have predicted you could have predicted 3, or you could have predicted 7. But both are 2 points away from what you're supposed to predict. So you want to make sure you don't care about the direction. So you don't care if the difference is +2 or -2. You only care about how far the difference is. That's why you're squaring up. And then you add up this error that you're getting on each point. So your sigma runs from I equal to 1 till the number of entries you have in your data set. So for each row, it's not n actually, it's the n that you have so it's basically going to be n by k, because you divided your 1,000 data set into 1,000 by 5 chunks. So this is 1,000 by 5, 200. So I equal to 1 to 200. And then what you want to do is, instead of doing this at a time and then like one row at a time and adding it, you want to do the same, but you want to add up all. That's why the sigma is running on each row at a time, right? First row predicted minus first row ground truth. How's the error? Plus second row, then I becomes 2. Second row predicted minus second row in ground truth. How did you do on the error? You're summing it all up, and then you're taking an average of this errors, which is going to be by n by k. With respect to the first fold or second fold or third fold. Obviously, the second fold, you're going to go from I equal to 201 till this is going to be 200 plus n by k. So it's going to be 201 till 400 and 401 till 500. But the first iteration that I was talking about in the entire 5-fold cross-validation completes once you compute the cross-validation, the prediction error on one fold at a time. So this is, let's call it the CV, since it's part of the cross-validation. This is the terminology, let's call it CV1, right? Then what you do in the next iteration is you have the CV1 is your RMSE error just in here that we did here. Now what you do in the second fold is very similar. This time, instead of dropping this guy, you drop this fellow in the second time, in the second iteration. And by drop, I mean this becomes your test. Okay. Now the rest of them. So now this guy comes back into the picture. This guy and these guys, these 3 folds, become your training chunk. Now I don't want to write it here because there's a lot of space, but the rest becomes the training chunk. So you train on this, you get a model, Now you predict on just by looking, while you train, you pass in X and Y from this chunk and this chunk correspondingly into it to train the model. Now since you have a predictive model, you can predict with it. Now how do you predict with it? You just pass the X input variables in the test chunk, and then you're predicting something that is supposed to look similar to these values. You'll see how similar they're looking, like I'm putting a mean square error on this chunk. So now you have CV2. So since this is the exact process, you're just repeating. You're going to do it 5 times. Next time you drop this guy, you train on the rest and predict on this. Now you drop this guy, train on the rest and predict on this. Now you drop this guy, train on this rest of 4 and then predict on this. So you have CV. So you have 5 CV errors. So basically, the complete cross-validation error is basically the average of those. So CVI by, you're doing it k times, right? And then you want to sum this up because that's what the average is. I equal to 1 to k. So CV1 plus CV2 plus CV3 plus CV4 plus CV5 errors averaged is your cross-validation error. Now, any questions at this point on this process?
One quick thing.
Yeah.
What is the total number of rows are not equally divisible?
Oh, okay. Yeah.
Like what is it? There are like 111 rows or something. Like
Yes. Yeah. So you're saying the even or odd thing, right? Yeah. So if you have an even number of rows, it's equally divisible. So if you have an odd number of rows, like 1,001 rows, and you're trying to divide by 5, so you obviously have a few leftovers. You can add them in. For now, it wouldn't matter unless it's an outlier row. You would add them on to whatever fold you want. It's perfectly okay for now.
Sorry, Pranita, I missed the last sentence.
Oh, you that reminder additional 1 or 2 rows that didn't get divisible, you add it in whatever chunk you want for now.
Oh, okay.
Yeah, that should be fine. The only time it would really be a mess is if it was an outlier row. But outlier is always a mess, not just for cross-validation.
Yeah.
By outlier, I mean it looks completely different from your outlier. Yeah.
All right, thanks.
Okay. So, and that would not matter, especially if you have a data set in the order of hundreds of thousands. If you have just 5 data points, then no point doing 5-fold cross-validation in here. Yeah. So you do that. So this is the cross-validation error. Now what we're doing is we can compute the cross. So can I change the screen? Okay. So we go to the next screen. Now you can compute cross-validation error as long as you can train a model. Because if you don't have a model, you can never compute a cross-validation error. So how do you do that? You would basically let's kind of zoom into the model part. So let's assume you have a model. Hold on. Let's assume you have a model that you can train, but how would you train a model? You also know that all these models take in data, obviously input data, take in output data. They also need parameters, which is the important thing. This is very important for our discussion now. Now these parameters, what are they influencing? They're influencing, are you fitting a very complicated fit or a smoother? Are you using a complicated family of functions that you're trying to choose which function to pick from? Or are you trying to choose a simple family of functions from which you pick a model from? Now, what does complicated or simple mean? It means literally something like this. So a complicated model is something that can fit these kind of curves. It's kind of crazy. It will go to a lot of data points. A simple model is like a straight line or something that's a little wavy like that, you know? So if the choice of P is going to decide, are you going to pick from these kind of curves or are you going to pick from these kind of curves? Even for SVM, you have those parameters. For SVM in specific, these parameters are the gamma and cost parameters. When we study SVM, we will see, again, we will zoom in internally for specifically when the model is SVM that you're trying to use and specifically the parameters are gamma and cost. What is SVM doing and how is it using gamma and cost? What are these parameters? How does it make a fit? Similar to linear regression, you know what linear regression is doing. You know its parameters are the slope and the intercept. But now you know what the influence of the slope and intercept is. But there's not much complicated model you can build because you're at the simplest level of models, is the linear model. Whatever your choice of slope and intercept, you're not going to fit something like this or like this. You're only fitting the right slope or the bad slope. But there's still Are you going to pass through most data points, or are you going to skip a few data points is a question. So that's the only amount of complexity you can control. But with SVM, you can go from these kind of complicated functions to these simple functions. There's a whole lot you can do based on your choice of P. We can study the internals of SVM, but we're at the cross-validation level of zooming in. So let's stay there because we need to understand the cross-validation part first. So now what you can do is, as long as you have some choice of parameters, say gamma equal to some instance, right? Gamma equal to 5, cost equal to 100, or cost equal to 1. Then your SVM is completely defined. You have data that is defined. You have some parameters you define. This function would work. Now you get some model between this high complexity and low complexity based on your choice of what these parameters would do. Now, what you want to do now is, since this is a completely well-defined function, now you have a properly usable model. Now, what you can do is you can compute the cross-validation error for this model. Now, this is the complete cross-validation error. This is the k-fold cross-validation error after you did the average of all those 5 folds of error. So it's basically what we saw in the previous screen. Now, what we can do is, the question is, you want to know what parameter to choose now, because you have something that works end-to-end. You have like a car that can run, but you need to choose whether you want to do the first gear or the fifth gear if it's a manual car, right? But if it's a complicated system, there's a lot more things you need to choose correctly for it to work. So that's what we're trying to see now. You have a model that will work end-to-end. If you've given a garbage parameter with respect to the data set, it will give you garbage out because it's not going to do any prediction properly, right? So you want to choose the right parameters to get the least cross-validation error. So that's the point. Now what you do is you take a grid of parameters of cost and gamma, because this is a discrete world. We are trying to do something discretely for now, as far as this assignment goes. So this is the cost, and say this is the gamma direction. So what am I meaning to say by that? Let me just break it down into a bunch of costs and gammas you could try. So this could be cost equal to 1, gamma equal to 1. This could be cost equal to 1, gamma equal to 0.5, and so on and so forth. So you have a bunch of things you can try as combinations of cost and gamma. So 2 numbers, one for the cost, one for gamma. You can try whatever. You can try cost equal to 1,000, gamma equal to 2,000. So you have some discrete set to start with. Now what you do is, for each choice of cost and gamma parameters, you want to compute, you want to fix that you would only use a model with a choice of cost equal to this and gamma equal to this particular combination in this particular box to start with. And for that combination you have, anyway, the data always stays the same. You have the data of x, train x, and y. You compute the cross-validation error, right? Now you can do that for every box. You have a bunch of different cross-validation errors, and then you choose the optimal parameters of cost and gamma. Okay, it's a little overkill, but anyway, that was supposed to be C star and gamma star. So those are the optimal parameters that gave you the least cross-validation error. That is how you choose your parameters for your SVM for a given data set. Now for another data set, you do the same process, but it'll end up choosing some other parameter that does the best, if it was a very different data set. Now, why are we doing this cross-validation again? There was a theoretical thing we were talking about, which is you don't want to overfit or underfit. So say x-axis is the complexity of the curve you're trying to fit, or the surface, or the high-dimensional surface you're trying to fit. So the cost and gamma in SVM controls this complexity from high complexity to low complexity. This is high complexity to low complexity. It could be other techniques, have other parameters. Now, for example, in neural networks, you need to choose at least the number of layers and the number of neurons, the learning rate. There are other parameters there internally. Now, this is the error. There are different kinds of errors you can measure, so I'm going to draw multiple plots. So your training error, if you did not do cross-validation, as your complexity increases, your training error almost goes to 0. Of course, it doesn't go less than 0, it goes to 0. Now, is it a good enough model because your error is almost 0 or like 0? Are we predicting 100% accuracy? No, not really, because this is only on your training set. Now, that's the set that you'd use to learn your model. Maybe it by-hearted the model a lot more, memorized it a lot more. Maybe it's going through every single point with too much of a complicated function than required for predicting properly on the test set. So now on the cross-validation error, where you're giving it 5 test sets that it has never seen 5 times, every time it's being trained, you're giving a test set that it has not seen, and you're averaging the errors. So then what's going to happen is you're going to have an error that goes down until the optimal complexity and then goes up. So maybe this is where you got the least error. So that is the level of complexity you want to use. So whatever cost and gamma gives you this this kind of error, which is this minimum cross-validation error, is the complexity you want to use for SVM. Now you have your data set, now you know what the parameters are, so your model is completely trained. You can put it in your company, lab, whatever, and start using it for your prediction. Under the assumption that you're getting similar data in terms of the phenomena that you're trying to model with respect to X and Y. If you train a model to predict who's going to be the next soccer game winner, and if you're giving it data from the hockey matches, obviously it's not going to work even if you trained it with cross-validation. That's the assumption that you're going to feed in match data from soccer match data when you apply it. Any questions at this point?
We have this kernel in this specific supervector machine. So can you also teach about the kernel trick, or are we going to learn it later in the course?
Yeah, that is part of the upcoming syllabus. However much we cover today and in the coming class as well. I have the slides.
Okay. And there's a little difference between SVM and logistic regression.
Mm-hmm.
Can you just, yeah.
Yeah, there's a lot of difference. So so the kernel trick comes up in the middle of this support vector machine slide. So we will get there, obviously, to your mostly maybe next class. So okay, so let's start with the logistic thing then. Before that, I have one question though. So in terms of the cross-validation process that I gave you, I told I described now, are you guys okay with the R side of things in terms of whether you're going to do it for loops or what kind of data frame?
Well,
you need some hints on that is another thing. If you need, we can do that later too.
Actually, I tried with the table and data frame. Mm-hmm. Do you have something else than these two, like dealing with the data? Like in Python, you have pickle and all these sort of things. So
you use the data frame for what part of it? Like for handling the data set, the X and Y data frame is good enough.
Yeah, that's what I use that for. But when I'm dividing between the data, like when I'm doing the initial division between 100 to say 1 to 100 as a testing set and the rest as training set, it's easier for me. And when I'm dividing the end of the data, say from 400 to 500 for testing and keeping the rest for training, it was going flexible. But when I was dealing with the data sets in between, middle of them, I was facing something. But yeah, I think if I try a little, I can.
Okay, then that's good. Yeah, I mean, I think then you're in the right path. Yeah. Going first. You can obviously do some Google searching or looking up syntaxes for the R functions. As long as you're understanding the code and doing it well, you guys have some experience on that, so that's good. All right, so then let's move to the question that Manish was asking. The logistic regression is a generalized linear model. So you're fitting curves of this kind. X transpose beta. X is your data set. Beta is the coefficients that you're trying to learn. And then what you're doing is you're applying a link function, which is the logit-related function for logistic regression, but it could be other things if it was another GLM. Okay, and then there is obviously some error that you won't be able to explain. But what are you explaining with this model? You're trying to explain what is the expected value of Y given this data X is what you're trying to explain here, right? So in specific to say the first row of your X data, if you took the first row of your X, which has a bunch of variables, you're trying to predict the expected value of what the first response is supposed to be, given that you observed the first row of X. So I equal to 1. You can take the second row, then you're trying to bring the second response, right? You're not using the third row to predict the response of the seventh row. That we're not doing anyway. So we do this. I mean, you're using it internally in terms of training, how you learn the beta, but in terms of this equation, this is what it is. When you try to predict it, already once you have the trained betas, already once you know the betas, this is how you're trying to use the prediction. Now, you're assuming that you're in generalized linear model, which is what logistic regression is a part of. You're assuming that your responses are modeled as a binomial distribution. So if you remember, a binomial distribution has a PDF, Gaussian has a PDF, say this is a Gaussian PDF, binomial has its own PDF, and every distribution has a mean. The continuous notion of mean is the expected value. Expected value is given by integral of x, p of x dx, right? All these concepts. You can also compute the variance using these integral kind of approaches, continuous approaches. So this is on average, given the probability of what you're observing, this is the average you would observe when you compute it. So you're trying to model your data as follows. You have data points. You're trying to fit, for every I, you're trying to fit some distribution. But you're trying to figure out, you want to fit a distribution of what mean. That's what you're trying to model. So on average, your average of this distribution would be your prediction. So if you fit the right distribution, the right mean, then that mean would be the prediction once you observe this. This is the logistic regression. There is these distributional assumptions and all this going on in here, right? You have these binomial assumptions. The way you're fitting the model is by maximizing the log likelihood of this model, all that kind of stuff. Since you have IID data, this is what you discussed before. SVM is very different. It's known as a discriminative model. There are generative and discriminative models. So in a discriminative model, what you do is this, which is a support vector machine, right? So what you're trying to do is, yeah, let me continue the drawing. So what you do is, say this was, say you had some x's and negatives, right? So say it's supposed to be an x. You're trying to find, in a linear SVM, there are lots of kinds of SVMs. You're trying to find a separator, a line that separates these two classes such that the margin that you have, say between this, let's assume this point did not exist to make it easier. Say this was another margin around that line. You're trying to see that the margin is of separation between these two classes is as maximum as possible. And obviously you have other parameters which will allow for doing a perfect separation to making a few errors in purpose, because maybe a perfect separation may result in overfitting. Maybe you're learning too much. Maybe you want to do little errors here and there, allow for some slack of error. So this is going to add in more parameters into the SVM. So this is the linear SVM. So here it's a very geometric kind of notion. GLM is, logistic regression is by foundationally a more statistical model. This is, of course, this is used by everyone. There's statistics that you can do a lot of analysis of SVMs and stuff, but the way the model works, here it's more like an optimization problem, trying to maximize the margin. You're trying to find these hyperplanes that maximize the margin of separation. So I have these notes for you that I put up for today's class, so which will show these things a little more clearly. So does this answer the question, or was there a specific reason you brought up the links between logistic and SVM? There's a more stronger link between logistic and a very special case of a neural network. And for a very special case, neural network would be a logistic regression if you used only one layer. But we didn't go to neural networks yet. Any other things you want to comment or ask around this direction, or some other things, Manish?
That's it. I guess.
Okay, good. So, all right. So let's go on into the presentation. Any other questions? Anyone else? Okay, so let's go into some of the presentation. We may not be covering all of this. We want to understand things at least to some reasonable extent in the first iteration. So we can spend some time, because the point is you're going to spend some part of the early coming week after the Sunday, and you're continuing your assignment as well, just also around SVM. So we're going to split this a little bit. Okay, so this is the kind of diagram I drew while showing you. Here I've only drawn one line. I've not drawn the margin of separation or anything yet. But if you want to compute the margin, it is this amount plus this amount. Anyway, it's not very clear right now. What it's showing here is you want to look for, in linear SVMs, you want to look for linear separators between the positive and the negative, between the two classes is what I'm showing here. So some terminology here, you're trying to fit the W transpose X plus B line in here. And then you want to use the sign of what's going to be your prediction, whether your point lies below the line or above this line. So if your prediction is below this line, then the sign of this function would be negative, because this is going to be, so this is not going to be 0 anymore. It's going to be -1, and here it's going to hit somewhere here. The above line, if your prediction was somewhere here, your calculation for W transpose X plus B for the same W transpose X would end up being greater than 0. If it ends up, so your intercept would be somewhere here, +1. Then it's going to be this particular class. So based on the sign of, if you choose the right W's and B's, the sign of the function that you're fitting will decide whether it's in a prediction phase, whether you would say it's positive predict this class or this class. So that's the very primary goal. But we're going to add a lot more. This is not SVM yet. This is definitely the equation that starts it a little bit. So the question, obviously, just how do you find the right separator, right? Are we overfitting or fitting? This is a very crude diagram. There's a lot of horrible things that can happen than this. But this is a good start to explain the point. You want to find the right answer, right? Just like in any model. So this is a little more like SVM here now. You're getting into more of the crux of it. So you want to fit the 0 W transpose equals 0 line. This is in this particular data set. Given the data set, this is your margin of separation that you have. Now you want to make sure this margin is as large as possible. The length, literally in your coordinate geometry classes, right? The +1, +2, or your 11th, 12th grade kind of thing. So you can always compute distance between two lines, right? Their formula spread. It's very well defined. So you want to maximize that distance as much as possible, and you want to come up with lines that do that, given this data set. So let's call that distance the margin. So it's the separation with support vector. So let's call it, use the row notation for it. Now, just to give you a heads up, if you want to measure a distance between a line, from a point to any given line, that's also there in coordinate geometry. There's a standard formula for it, and the formula will give you this result. If you had a line, there's a generic version actually, which is this is the answer of that formula, but basically the formula is, if your line was, say, ax plus b plus c equal to 0, that's the line, and plus by, sorry, ax plus by plus c equal to 0. It's a line in terms of x and y, and a, b, and c is what defines what line you're choosing. Now, if you had that, in your case, C0, now, since it's this vector multiplication, the A's and B's are in the W, so you're basically having a line called W1, X1 plus W2, X2. X2 is the Y, basically, if you had XY. Here you have X1, X2 instead. Same thing. Your two variables, instead of calling X and Y, you're calling X1. So that's the notation here, and this is the intercept kind of thing. There's your Y, X and Y coefficients are here. For that formula, basically the formula is you do, if you want to figure out the distance from a point xi, yi, you substitute that point in the line and then divide it by square root of the coefficients of your x1 and x2, which is what the norm is. Norm is doing w1 square plus w2 square if there's a line of two variables, for example. So anyway, it's a very simple formula. The point is not that, right? There's a formula for distance between two lines. There's a formula equation for computing distance between a point and a line. It's from very basic. So we have that. Think of it as some little gadgets that you have in trying to figure out how you estimate these lines in the machine learning setting. So that is this. There's the notion. Now, a little more. This is linear SVM. You can also, and so I gave you an example here by saying this is the 0 line, which is what it is. You can have the +1 line. You can have the -1 line. You don't have to have only the +1, -1, though. You can have the W transpose X plus B equal to 5 line, and you can have W transpose X plus B equal to -5 line as well. The question is, do you choose 5, 1, 5 and -5, or 1 and -1? What do you choose? That can be generalized to something called, say you want to have the row by 2, because here you're measuring the margin, so this is half length, half length. You want to have this, this is the margin, this thing is always going to be the center point, so these are your support vectors. So it's not going to be closer to one class or the other. So you want to, that's how the structure you're constraining your model to be have these properties before you learn what these parameters and how you figure out what the number should be for your data set. So you're generalizing it to the same concept, nothing else changing. So row by 2, negative row by 2. So now this picture is more well defined than in terms of equations. And this picture, all that structure didn't exist yet. It's just beginning there. So here, a little more well-defined. Now, this is what it is. So if your output was in -1 class, you want to have negative coming out. So if you did a sign of this, let's say there's a negative, if you have 1, you can have positive. Now, this is the same, the equivalence, same as if I multiplied it up with yi, negative becomes times negative becomes positive. Positive times positive is always positive. So mentioning these two is same as mentioning this condition. So having this condition as your model is same as having this condition, the product. So this is a little more mathematical, right? Or this is also mathematical, but you got rid of the if conditions and making it piecewise separate and stuff. So it's the same as this. Now, so you want to have this condition satisfied where your data is like this and your labels are saved. This is a binary classification answer. So this was the formula from any point. Now, your margin can be expressed, if you computed with those formulas, your margin would be, oops, hold on, sorry. Okay, do you see this little Google Hangout thing coming here? I guess you do. Yeah, that's probably because of the pen pointer. But anyway, what's in here, I'll tell you, it's a very small thing. What's in here is the formula for the margin, which you can completely compute. It's going to be this, 2 by the norm of omega. So this is the linear SVM. You want to maximize the margin, right? What was the margin? You want to maximize it. You want to find a W and B such that this is maximized. And for all your data set, this condition is satisfied. This is the same as saying you want to have 2 lines that separate the class 1 from class 2 based on their sign is the same as saying this. So you want to maximize the margin, satisfy this condition. That's the optimization problem. It's optimization because you have a maximization. A minimization could be another optimization problem. How do you, but anyway, that's not the point here. The point here is a maximization problem can be also, of this sort, can be made a minimization problem if you just made a reciprocal of it. So that's what they're looking at here. So you can minimize the norm. So minimizing the norm of W by 2 is the same as minimizing the norm of W. The 2 doesn't make any difference. This is the constant thing. So you want to minimize it. Again, you want to satisfy the same condition. So the maximization in terms of minimization. Now, it's also a quadratic optimization problem because it's an unknown function of squares involved. The degree involved is 2. The highest degree involved. The degree, which is the highest degree, is 2. So if it was just a linear equation that you're trying to maximize and minimize, then your objective function would be a linear optimization problem, which have a quadratic optimization problem. Okay, so same thing written again. Minimize this, satisfy the condition. Now we've gone to a little more optimization theory. We can get into the details. Let me do a quick time check at this standpoint. Okay, so we have 10 minutes. So let's go at this maybe at the similar pace. Do you have any questions till now? Okay.
No.
Okay, good. So let's continue at the same pace. So I think this seems to work. And however amount we cover that naturally. Let's not just rush up more and more. Okay, now the question is, okay, we have an quadratic optimization problem. Quadratic optimization problems are very common, very extensively studied. SVM, linear SVM is a quadratic optimization problem. It's just an instant example of it. And so there's a lot of mechanics and frameworks of how you can, find the optimal W's in these. So let me tell you a few things. Lagrange multipliers is an interesting concept which allows you to deal with constraints because you have an objective function, you have a constraint that your solution needs to satisfy while maximizing or minimizing the objective, in your case minimizing. So time to do some Lagrange multiplier drawing up. Or let me give you the, okay, yeah, let's do that. Let's do that. Okay. Back to the pen. We're doing red now. Okay. So if I have an objective that I want to maximize, say if the objective was f of x, but if f was a quadratic function, so it could be any quadratic function, x squared plus 2x minus 3, whatever. But if I have an objective and I want to find, but I also have a constraint set which I want to satisfy. These are the constraints. Some constraints. Maybe this could be multiple functions, but I put in say one function. say I want to satisfy some function of x that is supposed to be equal to 0. It could have been equal to -5, whatever. I could have C1, C2, I could have 10 functions. I want to find an x that maximizes this. So that is the same. This is some notation. I want to find the argument that maximizes this function. So that's what they call it. Argmax is what they use for notation. So what Lagrange multipliers does is this. Instead of it combines these two into this newer function. It calls it f of x, comma, let's call it lambda. I'm bringing a new thing called lambda here, equal to f of x plus lambda c of x. So basically, you want to the lambda is what we're going to figure out as well. But lambda is, if it was say a very big number, it's trying to make sure. So okay, you're trying to maximize this function now. So if a lambda is a very big number, you're trying to make sure that you're maximizing f of x, but at the same time you're making sure, since lambda is a very big number, this condition is also satisfied. Because if this is not satisfied, you're going to have a big penalty of this. So it's going to make it harder. It's going to make it harder for you to maximize this problem. So the theory says you solve instead of solving for this, since it was quadratic function, what you can do is you take the derivative of f of x with respect to x. So it will be a function of lambdas, and you'll have something to do with x as well. And then you also take the derivative with respect to lambda. So what you have is df of x. Sorry, you don't do it. I mean, you can do it with lambda, but what it basically means is you ignore all of this because you're doing the rate of change as lambda. All you would get is just the c of x, the solution. So basically, this same as saying you take c of x, the equation. You solve for these two. These two are functions of x and lambda. You can get the optimal x and lambda. So it'll tell you what amount of penalty you need to put here, and then what x is ending up to maximize this problem while satisfying this constraint. So this is Lagrange multiplier technique. We can go into why this is working a little more deeper, but I want to stick a little to the point. This is just another gadget that you're having. Imagine it's like your coordinate geometry thing. You can always question me on why it works. We can spend more time as well on that if you're really interested about it. So we have that gadget now. So the same concept. Now there's a concept also of dual problem and of duality in optimization. So optimization is a strong graduate level or like a PhD level area in itself. There are books and different kinds of optimization. It's just like machine learning, optimization. Both are two very huge fields. So and there's a concept of duality in optimization problems. So what that says is dual means there are two things, right? So it basically says you can always convert your problem into a dual problem, and then the solution of the dual problem. And then you also have some small transformation. So what you do is you solve the dual problem instead, and then you apply that transformation that goes along with that duality, and then you would get, it will automatically be the solution of your original problem. So that's what the concept of duality is. Okay, so for example, the Lagrange multiplier is a special example of a duality. Instead of solving the original problem, we solve some other problem, but that solution ends up to be the solution of your original problem, right? It's like an auxiliary thing, or like a surrogate that you're using. So that's what he meant. There's some duality involved, but there's some duality theory involved as well. So, one way to do this is you want to make this as a function of alphas, similar to lambdas, and then you want to solve this problem. And then if you maximize this problem instead and find the right alphas, then you can come up with the original solutions, which is what you want, right? This is the transformation. So this is the dual answer. This is the solution for the dual using the Lagrange multiplier technique. And then this is the transformation he's telling you to apply to the optimal solution of the dual problem. The solution to the dual problem, you apply this transformation. The primal problem is your original problem. Then you get the optimal solution which is the W's and B's that will solve your original problem, which is the primal problem. So there's a lot of theory involved here, optimization theory. In optimization, you have this concept of primal problem, dual problem. Solve the dual problem, apply some newer transformation that goes along with it on the solution of the dual problem. That solution will automatically, it's a theorem, end up being the solution of the primal problem. Now, will it satisfy whatever combination of problems? Will I always have a dual and transform? Not necessarily. There are some conditions you need to satisfy. These are called the regularity conditions in optimization, but that's not the point of this slide. It's more trying to see how you're borrowing some theory from optimization, the math in optimization, in trying to solve your SVM. But we can always go into that at any point. I'm just giving you a hunch, or you can read it up a little more as well. If you want to understand what those conditions are, the regularity conditions and Slater conditions, etc. So this is the mechanics involved here. So now you have the solution for W and D. So now that will be your optimal solution for your classification. So as long as you have the right alphas from the duals, you're applying it in this form, you'll have the optimal solution. Now it's just interesting to see that you're using this inner product, xi transpose x. This will help us later when we go into the kernel trick, which Manish was asking a little about, which doesn't. So here the kernel is basically just this function. It's kind of a more simpler function, but you can apply more complicated functions of x transpose x in the future, which is what's going to happen in the kernel trick. So we will get there when we get there. A few more slides, maybe mostly in the next class. So any questions here on the direction of what we are borrowing from where and why we're doing it and how it works?
I think we have to read through it once. Then we might come up with some questions.
I agree. Yeah, I agree. Yep, definitely. There's a lot to read around these areas. So now the question is, we don't want to fit the exact fit, but what we want to do, you don't want the exact fit. You're allowing for a little more errors that you can make while coming up with the optimal solution of these support vectors. So that's what it's showing in here. Why are we doing this? This is again to have some mechanism to control for the complexity of your fit. If your epsilons were very low, and if that is good enough, and you still have a good cross-validation error, which is a good measure of error for future performance, then you're okay. But if your cross-validation error is very bad, then maybe if you're overfitting, you want to increase this room for error so that you can fit a little more simpler functions. But if you're underfitting, you can decrease this amount of slack you're allowing for. This is the amount of approximation you're allowing for while searching for the support vectors. Instead of finding the exact support vectors, he's saying find some support vector that maximizes the margin again, but making sure it is within this amount of slack or approximation that you can make. So this is giving you this parameter to control between overfitting and underfitting. At least one mechanism. There are other mechanisms that you can use, but that will give you other parameters like gamma and stuff and cost. So cost is basically something to do with this. So how much cost you're allowing to pay in terms of the slack. So that's the cost variable in your SVM-NR. There's obviously the gamma variable, but that usually comes up in nonlinear SVM. So there's no gamma in linear SVM. There's only cost. Soft margin, same framework. So again, you have this quadratic problem that you want to minimize, which is going to maximize the margin because it was a reciprocal. You want to satisfy these conditions, which will make sure which is same as saying the product is going to give you a sign of -1 if it's class other one class, and if it's a +1 if it's other class. It's the same as doing this product test then. We talked about this 3 slides back. So you have that. Now all we're doing is we're adding in slack variables, which is where the cost is coming in. This is the C. This is what is the C that you're using in R in your SVM function. So based on the choice of amount of cost you're willing to take. If you can take a lot of cost, then if you're starting with a slack of 1, if your cost was 5, then you're literally saying I'm allowing to take an approximation of +5 or -5 of error. That's still okay. So you want to decide how much C you want to use in terms of overfitting or underfitting or optimal fitting by cross-validation, obviously. So it will automatically decide how much of slack is optimal for you to learn the right amount of prediction and generalize the function instead of overfitting or underfitting. So same thing happened to this equation like we saw in the before slide. The epsilons came into this picture. So parameter C can be viewed as a way to control overfitting. It trades off basically the relative importance of maximizing the margin, which is your main objective, and also making sure you're not overfitting or underfitting. Remember, you had another parameter, gamma, and that's going to come in the second half, which is basically the second half of the show in here for the SVMs, which is the nonlinear SVMs. That's where you learn what this gamma parameter is, how it's working internally. Now you have an understanding on the math side as well, the programming that you're trying to finish for your assignment in terms of cost and gamma. Now the soft margin solution as well is again the dual problem like I showed you. So the alphas come up. You have a primal problem. Now there's a dual problem, which is this. So the theory from optimization that we're trying to borrow is instead of optimizing the primal problem, we're optimizing the dual problem, and then we apply a transformation, which is this. So when you apply that transformation to the solution of the dual problem, you will end up getting a solution that automatically solves the primal problem. So the same thing has been applied here. Okay, and then the constraints are again handled using the Lagrange multipliers, like I showed you when I did the equations there. Again, the solution, it's interesting to note that X transpose X is playing an important role even in the solution with the slack variables, which is a soft margin linear SVM classification solution. So this is a good, interesting that we stopped at the right point because now we're moving to the second phase to the nonlinear SVM, which will happen in the second part of the talk next week. So if you have other questions, and then any questions on this now, or are we good for now? I understand you want to do some more reading and research as well. So what we're going to do is we're going to do the same thing pattern, I guess. Next week, again, you start with questions like you asked this time. Go in order and see what's bothering you, or where you get stuck, or what you've done well. And we're going to cover those, and then we're going to cover in the rest of the class the second part of the SVM, which is nonlinear SVM. That's where you learn what the gamma function is doing. Sorry, the gamma parameter is doing in terms of internals. So yeah, calling it a day. I think we can stop recording.
Hey Praneeth.
Go ahead.
In the next class, can you just tell us about what you do in your general day-to-day life as a data scientist? Like, how is the production code going to look in?
Sure. Yeah. I can. I can tell you. How it works in in large-scale companies, and how it works in mid or like startup-y stuff as well. So yeah, we can cover that in the next class for sure. Let's keep some room for that too.
Yep. Thank you.
All right. So yep, let's call it a day. I guess we can officially stop recording at this point.